My name is Alex Kinghorn, and the topic of this project is stable and unstable convection in water near its maximum density. Stable and unstable convection are two types of free convection. Free convection is buoyancy driven, meaning that as a fluid changes temperature, it will change density, causing convective currents which causes heat transfer. In the cases seen to the right, with the ice on the top, a warmer fluid will experience unstable convection, which can be modeled by the top equation. With the ice on the bottom, a warmer fluid will experience stable convection, which can be modeled by the bottom equation. These Nusselt numbers are analogous to their respective heat transfer rates and have a difference of a factor of 2. An experiment was conducted to measure and compare stable and unstable convection. Two types of specimens were frozen, one normal and the other with a small weight. The first specimen floated and the other didn't. 4 rounds of tests were performed at differing initial water temperatures. Each round used 10 styrofoam cups to hold 5 floating and 5 not floating specimens. Equal amounts of water were poured into each cup and specimens were placed inside. The time it took each specimen to melt was recorded and then averaged for each round. The results of the experiment can be seen here. An overall trend for increasing fractional difference with increasing water temperature can be seen. As discussed before, with these two cases, it should show stable versus unstable convection with fractional difference of 2. However, looking at the results, it can be seen that for the most part, the prediction of 2 is off, with the water temperature of 12 degrees Celsius being the closest. Water reaches its maximum density at 4 degrees Celsius. This means that it doesn't change its density with temperature linearly and becomes less dense, changing from 4 degrees Celsius to 0 degrees Celsius. Because of this, the buoyancy-driven free convection will inverse for water below 4 degrees Celsius. After running the tests, it was determined that some of the water was reaching temperatures below 4 degrees Celsius. The figure to the right shows the change in the stable Nusselt number as the film temperature approaches the maximum density. The Nusselt number approaches 0 as the film temperature approaches 4. Because of this inversion, it can be assumed that the heat transfer for the test looked more like what is seen here. There is an area of inverted free convection until the temperature reaches 4 degrees Celsius, and then the regular convection for temperatures above 4 degrees Celsius. Using this new analysis, new calculations can be made to find more accurate fractional differences for each case. It was assumed that there would be insignificant heat transfer effects from phase change, no effects from the interaction between stable and unstable layers, the styrofoam cups perfectly insulates the system, and the weight in the one specimen is the same temperature as the ice and does not affect heat transfer. For the floating specimen, it was assumed that the stable layer was unable to form due to the unstable layer, so only unstable convection in the water was considered. This was also shown while measuring the water temperature at various depths during the melting process. Also, heat transfer between the ice and the air is taken into consideration. The equation for heat flux is shown. For the not floating specimen, it was assumed that the unstable layer was able to form due to a weak stable layer. This was also shown while measuring the water temperature at various depths during the melting process. Heat transfer between the ice and the air was neglected due to insignificant temperature difference. The new calculated fractional difference is the difference between the floating and not floating heat fluxes. Heat flux is analogous to the rate of heat transfer each will see, and thus can be compared to the melt times fractional difference. As can be seen, these values more closely match the lower initial temperature, but the higher initial temperatures are still about 25% off. In the not floating test, it was observed that as the water temperature increased, the layer between the ice and the level at which the water reached 4 degrees Celsius consistently got smaller. Because this layer is thin, it can be assumed heat transfer through conduction rather than unstable conduction as before. This gives the equation shown. Using this new equation with an assumed layer thickness of 4 millimeters, the fractional difference is now within about 11%. While the calculated values using conduction analysis got closer to the measured values, further considerations for conduction is needed. For example, what is the critical layer thickness? Also, using this new conduction equation, it would be expected to see an increase in flux with decreasing layer thickness. However, the experiments contradicted this and showed that as the layer thickness decreased, the overall heat transfer decreased as well. In conclusion, the heat transfer for these two cases is similar to unstable and stable convection, but is complicated by having maximum density at 4 degrees Celsius. Using a more accurate representation of inverted and regular convection resulted in a closer match to the measured data. Taking conduction into consideration for the high initial water temperatures resulted in an even closer match. These more accurate analyses resulted in a model that produced a data match of within about 5 to 11% error. Further studies into the effects due to phase change, layer thickness, conduction, and any interaction between stable and unstable convective layers would yield an even more accurate model.